Okay, maybe we can start. So for the second talk in this morning, it's our great honor to have Professor Yuri Tschinkel from New York University. Let's welcome. He will talk about rationality problems.
Thank you, and also thanks to the organizers for inviting me to speak here. So we'll start with the introduction. Rationality in algebra means we consider fields, capital K over some ground fields, and we say such a field is rational if it's a purely transcendental extension of the ground field. Now, in geometry, an algebraic variety is rational if the function field is rational. So, birationality to projective space, standard reference variety. And the notion very much depends on the ground field K, as I will explain. So, the basic example is the case of conics. You look at rational solutions of this equation that we've seen already. And so, things are parametrized by these rational. And, well, the way you think about it geometrically, the way the Greeks thought about it, you pick one point, and then you draw lines through that point with rational slopes, and the other intersection point, well, it's a quadratic equation, you know one root is rational, the other is also rational, and that's how you parameterize all rational points on that conic. And you can do the same thing with the quadric, you pick a rational point, you start drawing lines, but then you realize that, well, some lines will be completely contained in the quadric, and so that means that all lines will give you a second intersection point, and that's birationality. So for almost all lines, you hit it. And so let me give you another geometric construction, cubic surfaces with two disjoint lines. You may know that there are 27 lines over, let's say, algebraic closure, but over the ground field, you may not have all the 27. Now, suppose you have two disjoint. Well, take one line and look at all planes through that line. So it will intersect the cubic surface and a cubic curve. You have a line already in that intersection, so the residual will be a conic. As you move the planes, you'll get a conic bundle over P1. Now, the other line, well, it's not in that plane. I mean, it's not in the same plane with the line that you start out with, so it will intersect in one point, all these other planes, and that point is not on the original line, so it must be in a conic. So every conic in that family, you get a distinguished point. Well, that tells you that that conic bundle over P1, now considered as a conic over the nonclosed fields, a function field of P1, well, will have a point. And then you apply the previous construction that told you that if you have a conic with a point, that's birational, well, it's homomorphic to P1, and so this is how you construct rationality for a cubic surface. And you can do the similar thing for cubic hypersurfaces with an isolated singularity. Again, you start drawing lines through that singularity, if the singularity is over the ground field. Now, so that's geometry. How do you parameterize? How do you write down parametrizing forms, polynomials, let's say for this particular cubic surface? So Nomelkis did it, and this is what you get. And so you will agree with me that trying to guess these kind of parametrizing equations is hopeless. And so that's why, you know, that the 2 points of view, geometry, and then of course the algebra in the background, well, you should sort of keep in mind what it is. So this is rationality for that cubic surface. But now how about this one? You change one coefficient, and you think, well, can you do something like this? And it turns out that you cannot. So not only with these kind of forms, but no, and a priori, of course, there is no limit on what kind of degrees you would have to pick and so on and so on. Well, how do we know this? Well, there is some hidden symmetry in the picture. The Galois group is acting on the 27 lines that you can write down simply by grouping those variables correspondingly. And there is a logical abstraction in the picture that you can compute. And in this case, it will tell you that over the ground field, this cubic surface is not rational. Now, let me start with something completely different a priori. calculus 2, you learn how to integrate. Let's integrate this function over the p-adics. So maximum and p-adic absolute value of the number. And so the p-adics, we're going to split. This is a domain. So those are the integers. And then we fix the p-adic absolute value. And then the volume of the domain is p to the j minus p to the j minus 1, the previous one. So, and the integration will therefore be this sum. So here the function that we integrate is 1, and there the function is, well, this to the power j. And so as you can imagine, it's a geometric series, so 1 plus something like this. And I did the summation for you, and this is what you get. Now, let's put s equals to 2 in this picture. What do we find? 1 plus 1 over p, and that's the number of points over the finite field on p1 divided by p to the 1, which is a dimension. So what's the moral? We're integrating over the open piece, the affine line, the p-adic points on the affine line, and we're learning something about the closure, about P1. So this is actually a volume with respect to some natural measure that can be defined in generality. So let's start with some smooth projective variety of dimension n over a number field. Then, well, with some choices, metrization of the canonical line bundle and so on, you can define a Tamagawa measure. When you integrate this measure over the p-adic points of any Zariski open, you find that, well, it's the same thing as the integral over the closure, over the p-adic points of the closure being projective. It's the same thing as integrating over the integers. And that integration you can split into a finite sum of points over a finite field of these kind of things, and all of these things contribute the same thing to the integral. So you're counting points over finite field by integrating. Now, the way you should think about this integration is, well, you can integrate over a closed interval or an open interval, and if the thing is convergent, the boundary doesn't matter, and this is the same thing here. Now, what are the applications of this idea? That's right. I just explained that if you a measure that converges, then the boundary doesn't matter. The boundary is measure 0. That's a miracle, and this is how you apply it. Okay, so suppose you have birational Calabi-Yau varieties of dimension n over, let's say, number field. The canonical line bundle is trivial. It has a canonical metrization. You get these measures quite naturally. And as I just explained, you integrate that measure over the p-adic points, and you get the number of points over a finite field. Suppose you have two birational Calabi-Yau varieties. That was like the Battery's observation. Then you start integrating. Well, on the one hand, you get the number of fp points or fq points on x. Why this integral? But I've just explained to you that it's actually the same integral in both cases. And so, well, you get to compare number of fq points on x and on y, and you have it for almost all places and all q. So you can conclude that birational Calabi-Yaus have equal Betti numbers, and you can learn more about this. And that was the starting point of motivic integration. Maxim Kontsevich observed that you can do it more generally, not necessarily of the p-adics. So these kind of integrals, the p-adic integrals, Iguza type integrals, they play an important role. I just told you that, well, you can extract invariants, things that don't depend on the compactification chosen. So in particular, if you like, you can learn about singularities. So no matter what the desingularization is, once you have something convergent, well, the integral will be the same. And of course, the way I ran into these things from my earlier work on Mani's conjecture, analytic number theory, so these integrals play a central role in analytic spectral approaches to height zeta functions and so on, well, you just run into this computing volume asymptotics p-adically, adelically, and so on. Now, how does that relate to rationality problems? And of course, the things that's always been of interest to me, how much arithmetic is encoded in geometry, and conversely, how much geometry can you read off from arithmetic. And I just showed you how from integrals or from counting points over finite fields, you learn something about the geometry, Calabi-Yau's topology. So let's go back. Rationality means you're birational to Pn. There is a related notion, which is stable rationality. That is rationality after you multiply with a reference variety projective space. And a priori, it's not clear at all how to produce these kind of varieties that are not rational but are stably rational, but you can do that with the complex numbers as well. Like a big breakthrough in the study of rationality was the work of Voisin based on prior work of Bloch and Srinivas related to some abstractions to stable rationality under the name of integral decomposition of the diagonal. I don't define this. An extension of this work by Koryotolin and Perutka in terms of universal Chow-zero triviality, and they directly, Nikes and Schindler, realized that, well, there is something that also specializes K0R, model as a class of the affine line. I'll talk about it in a second. And very soon after that preprint appeared on Archive, Maxim Kutsevich and I realized that, well, there is yet another thing which also specializes. This idea that you can specialize some abstractions to stable rationality or rationality that led to many, many developments and many results in birational geometry. For example, the result of Koryotolin and Perutka says that a very general smooth quartic threefold is not stably rational. A famous theorem from the 70s of Manin and Laskovsky said that, well, a smooth quartic threefold is not rational. But stable rationality is much more subtle rationality. And in fact, the technique to prove the failure of rationality for smooth quartic, birational rigidity, well, it's very unstable in a sense that you start multiplying its projective space and rigidity completely disappears. Now, also led to a result I reported on last year, namely variation of stable rationality in smooth families. You can produce families of four-folds, three-folds, where properties jump from fiber to fiber. And then, well, it allowed to settle the problem of stable rationality for very general Fano threefolds. All non-rational ones, with the exception of the cubic threefold and another Fano threefold that's birational to it, X14, all of those non-rational ones are actually, the very general ones, also not stably rational. But I want to talk about what's the technique and how does it work. So Larson and Luntz observed already 20 years ago that this group K0R, the ideal generated by the class of the affine line, is isomorphic to the free abelian group on equivalence classes of algebraic varieties modulo stable rationality. So result went unnoticed for a long time, but it's a really fundamental thing. The proof is very short, almost straightforward. And then Nikes and Schindler noticed that something that was also out there, namely a special morphism for this K0R mod L, which is sort of motivic measures. This is where motivic measures live. Well, this kind of specialization formula, inspired by work of Kazhdan Khrushchevsky and Deneb-Lazare and others, says that, okay, there is such a homomorphism from the one-on power series to the residue field here, and, well, it's out there and used, and once you know that the group is the group of classes of stable rationality, then you see that stable rationality specializes. And Maxim and I realized that, well, the formula that appeared here, you can refine it to produce specialization of rationality directly. So this Bern K is a free abelian group on equivalence classes of algebraic varieties up to rationality rather than stable rationality. And why do we call it Bern? Well, it's graded by dimension 0. What is Bern 0? It's zero-dimensional varieties, which are, well, finite extensions of your ground field K. So that's finite index subgroup in the absolute Galois group, up to conjugation. Anyway, that was...
Yuri, good question. So if the image is not zero, then the original, our big K is not...
That's the whole point. Yeah. So, of course, you have to be careful because your special fiber, it could be singular, there could be components, and so on and so on. But this is the idea, the specialization of personality. And I'm showing you how this thing comes about. So let's be specific. Okay, so we look at Laurent power series, the integers, the residue field. What's important here is characteristic 0, because, well, we use weak factorization in all these arguments, not available as positive characteristic. And so you look at some variety over this big field, Laurent power series, you choose a model. And, well, you write down the special fiber. There could be some multiplicities here, but you ignore them. Amazingly, it works. And then you write down this kind of formula. Now, that formula, so it's like integrating. It's, well, you look at the boundary, which in this case is this, and you're just counting if q points on the boundary, if you like, stratum by stratum by stratum. It's an integral. Once you realize that this is an integral, you know it doesn't depend on the model. It doesn't depend on the compactification. It doesn't depend on birational issues. It really is an invariant. Now, of course, the way you prove it, because we don't really know that this is an integral, once you have such a formula, you have to verify it, and you use weak factorization, blowing up, blowing down, so blowing up smooth subvarieties and so on, blowing down pieces of the boundary, and then you compute. And it's consistent. It must be consistent. You already know that. And so that's it. Because exactly. So, well, and so, yeah, well, because it's a periodic integral in disguise. But the formula you have to verify directly, geometrically. Now, where does it lead us to? So, the way I'm thinking about rationality or non-closed fields, well, you look at the Galois group acting on all your special loci, cubic surface, 27 lines, there is some Galois group in the background, and there are very close similarities in that story with what you see when you look at varieties with symmetries. In other words, you work over algebraically closed fields, but now consider actions of, let's say, finite automorphisms on your variety. Now, that point of view goes back to Manning. First papers on this subject already talked about G varieties, where G was Galois group and automorphisms. And so there is an enormous literature already in dimension 2. Of course, Manning, Niskovsky, and Bogomolov, Talent, Dolgachev, Blanc, Prokhorov, Chelsov, many people worked on this. And knowing that, well, we saw that this kind of civic integration approach yielded results. So why not look for some ways to integrate in presence of actions of finite groups and see what happens? And so, well, I told you what rationality is of a non-closed field, and of course rationality implies stable rationality, but what would the analog be in equivariant geometry? So the analog of projective space in equivariant geometry would be, I take my finite group G, I look at some representation, I projectivize, if I'm lucky, I get a G action on that projective space, and then I could say, well, if my G variety X, a variety with an action of my finite group G, generically free, maybe regular on some model, if it's birational to a projectivization of a representation, then I will call that variety linearizable or linear, if you like. Now, stable linearizability in this setup would be I take my variety, I multiply with the projective space, and now I have to be I have to think about projective space. Do I put trivial action here or non-trivial action? Let's say trivial action. For today, it will be projective space with trivial action. And then I will say that something like this is stably linear. Well, if that is linear in the sense of the previous definition. Okay. Now, of course, linear or linearizable implies stably linearizable. Now, so what are the similarities between these points of view? Well, if I have a variety of a non-closed field, the absolute Galois group will act on all special loci, on the singularities, on the geometric Picard group, on the Brown group over the closure, on everything inside. Now, if I have a G action on a variety of an algebraically closed field, well, then that G will also act on all these loci, and correspondingly, the abstractions from the action that I would see from, let's say, Galois action and the G action would be similar. And one of the abstractions to rationality and to linearizability comes about from considerations of the Picard group. The Picard group of projective space, of course, is Z, and if you want to blow up, then you blow up a G orbit or a Galois orbit, and if you add to Z a permutation module, then H1 doesn't change. Well, there is this notion of stably permutation, namely adding a permutation, taking out a permutation, and so on and so on. So something that's rational over the ground field or linearizable in presence of G actions has the property that the Picard has to be a stable permutation module. Stable permutation is if you add a permutation module, you're a permutation module or some permutation modules. Yeah? Add, subtract, so stably, up to addition of a permutation module. So, and those are the same abstractions. Now it turns out, I was asking around, is there an effective algorithm to decide whether a given G module, torsion-free Z module, is a stable permutation module? And apparently it's not really known, strangely, but there is a computable abstraction, namely the vanishing of cohomologies, the first cohomology. For a permutation module, a stable permutation module, that has to be zero. So if you suddenly find that this is not zero, then it can't be rational or linearizable. And that is the abstraction that happens for the diagonal cubic surface with coefficient 2 that I showed you before. That is precisely it. And that abstraction is computable once you know the action on the Picard group. All right. And moreover, it's a stable birational invariant. Namely, if you multiply this projective space or projectivization of a G representation, you don't change that H1. And so once it's non-zero, you know that your variety is not rational or not stable linearizable. We are looking at birational. So we are looking at birationality. So my theory is birational. It's a birational invariant. In other words, when you start blowing up, blowing down, blowing up, blowing down, you add, subtract the permutation module, and that doesn't change H1. Okay? And same thing for products. So just compute the Picard group of a product, and that's what you get. Now, so those are the similarities. But there are also crucial differences in that picture. Namely, if I have a rational variety of a non-closed field, at least I have to have rational points. So conic without points doesn't work. But if I have a variety with a G action, then having the analog of a rational point with fixed point under my group G, like a rational point is fixed under the Galois group, if you like, well, that's not a birational invariant for non-abelian groups. And there is a very simple way of seeing this. Take your favorite non-abelian group, let's say S3, symmetric group on 3, yeah? And it's two-dimensional representation. Well, it fixes the origin, obviously. Now blow up that origin, what do you get? Projectivization of that two-dimensional representation. Well, there are no fixed points. So you had a fixed point originally, you blow up, no fixed points. So that is a very relevant thing, especially if your rationality constructions rely on existence of some, rational points or fixed points. Now, there's another difference that at first doesn't strike you as a difference. Well, there is only one projective space over a field. But there are many representations of the same group, of the same dimension. So a priori, you could have the action of the same finite group on projective space of the same dimension. And how do you know these actions are birational? And in fact, there are non-birational actions. So, okay, so let's go through the examples that we looked at. Of course, a conic is rational if and only if it's stably rational, if and only if there is a rational point. Now, how about the G action on P1? So what acts on P1? Cyclic, dihedral, like 4 is 45. Well, so here is a simple observation. The action is linearizable if and only if it's stably linearizable, if and only if it's the group that's acting is a cyclic group or the dihedral group is odd n. So let's talk through this. There is a Z2 plus Z2 action on P1. X goes to minus x goes to 1 over x. I'll try to make that action linear. So we would need a two-dimensional representation of Z2 squared so that when I projectivize it, I get the given action on P1. Well, you can't, because if you do two-dimensional representation of Z2 squared, necessarily one of the Z2s in that group will act diagonally, so when you projectivize, you don't get the Z2 squared to act. So to get the Z2 square action that we see, you have to look at the dihedral group. And so, and it's two-dimensional representations that you would then projectivize. All right, so that's P1. Well,
Because you see the second last exercise.
yeah.
The second can be checked.
Of course. So, so this is to tell you about linear versus projectable linear actions, okay? Now, quadrics, let's see. Again, over non-closed field, you have a rational point, rational, and it's stably rational if and only if. How about quadrics in sort of higher dimensions with actions of finite groups? Well, the first thing that you learn that there are linearizable actions on quadrics without fixed points. Okay, maybe you're not surprised. But how about quadric surfaces? Well, you find non-linearizable actions, but stably linearizable actions on quadric surfaces. And in fact, Brendan Hassett and I, settled it completely. We know all the actions that are stably linearizable and so on. Now, how about quadric threefolds? Okay, let me give you this particular quadric threefold, very explicit equation. And let's say I work with a dihedral group of order 10. I mean, how would I act on this? So I act trivially on this coordinate. Okay, now I can switch these two and act by character. So that would be a two-dimensional representation of my dihedral group. And so I can projectivize that representation, and then I'll get an action. So, well, how can I cook up this five-dimensional thing? Well, I can take two different representations of the dihedral group and projectivize. Or I could take two of the same, right, and then projectivize. I have two representations, reducible, faithful two-dimensional representations. Well, for those actions, for this action, linearizability is known. There are no fixed points. For that action, we don't know it. We have no abstractions, we have no idea. We don't know how to check it. Is it linearizable? Is it not linearizable? So here is a challenge problem. Three-dimensional quadric, this is what you have. And of course, in higher dimensions, quadrics in presence of G actions, I think that's pretty much all. It doesn't work. Nothing that we can think of works. Now, of course, the Picard is Z. The G action on Picard doesn't produce cohomology anything. So all abstractions that were visible, available, fail in this case. All right. So the basic problem, therefore, how do we distinguish birational types of actions? How do we distinguish nonlinear actions from linear actions? And then how do we distinguish sort of linear actions up to birationality? So even subgroups of PGL3, where you take a group and you embed it differently, if you like, into PGL3, you get different actions of the same group on P2. Well, when are they birational to each other? That's still open. So, of course, all finite subgroups of PGL3 up to conjugation PGL3 are known for 120 years or so more. But how about up to conjugation in the Cremona group? So that's still open. And now I'm going to talk about some new invariants, inspired, if you like, by motivic integration, that allow to distinguish some actions, even actions too, that were not distinguishable before. Okay, so what kind of invariants do we have? Well, the cohomology action, the H1 G action on Picard, we already talked about as stable birational invariant. I'm going to talk about some new invariants. Well, so here is a result from 20 years ago. You look at abelian groups and you look at linear representations. Let's say you have an abelian group of rank at most D, and you look at the D-dimensional representation. So what do you see? Well, you see the characters of the representation. So, okay, you compute the determinant. And the theorem is that these actions on affine space of dimension D are equivariantly birational if and only if the determinants differ by plus minus 1. In particular, you see that if the rank is strictly less than the dimension, then the determinant is going to be 0. And so, well, 0 is 0. Therefore, all such actions are equivariantly birational. So all cyclic groups acting on projective space of dimension at least 2 are equivariantly birational. Okay? Now, so Maxime and I decided to look at actions of abelian groups. And what do you see when you see an action? You see fixed points or fixed strata fixed by the group action. And then what do you see? Well, you stratify the fixed locus, that is joint union of subvarieties. You pick a point inside your locus, and then the group action has to go somewhere. If it's not acting on the variety, it has to act in the tangent bundle, normal bundle to the point. So you record all the eigenvalues, and you just write down what you see. So you look at symbols. So these are the eigenvalues for the action, which are characters of your group, abelian group. So it's an n tuple of characters. And so you have this assignment from variety to this sum, finite sum of such symbols. Now, okay, let's act on P2. All right, on P2. So we act X, Y, Z, and we act with characters, let's say zeta to the A, zeta to the B, and then, well, we record those, like as 3 fixed points, A not equal to B. So 1, 0, 0, 0, 1, 0, 0, 0, 1, and at each fixed point you record the eigenvalues. So what would be the eigenvalues be? So in action of a cyclic group on P2, well, you would see AB, and then you would see all the other ones. And since we know that all those actions are the same, it's sort of natural to declare that the sum of these 3 things, which would be the 3 contributions from the 3 fixed points, that should be 0. And, well, we just declare it to be 0. Now, we see such a symbol, and we see the signs here and there. They say, okay, let's move the sign in. So let's say that AB is minus A minus B, and let's say that AB is A, well, then B minus A, and A minus BB. So, okay, so let's define the group. We look at residues mod n, so these are the n roots of unity that would act on my P2, and we record the 2 roots that we see at each fixed point. And so, of course, I have to generate the group. So GCD, A, B, and N has to be 1. Now, when I see those weights in the tangent space, well, I don't know which comes first, which comes second. So, of course, AB is equal to BA. And so then that's the relation that I just wrote down. And then, well, if I see AA, in other words, well, then it's the same thing as A0. This is sort of, I have along a line. Yeah, so, okay. Now, so how many generators? The number of generators is the number of residues, so it's like n squared. And how many relations for each such thing? I have a relation. So I have like n squared generators, n squared relations. About, how do I know I get anything? Well, so when n is prime, we find this. So of course, the first couple of terms you compute it by hand, and you run the computer, and then you see this formula, and you say, wait a minute, 24. Like I see AB equals BA, I can think about 2, I can think about 4. Where does the 3 come from? And so the moment you see 24, you think, and in fact, well, I'll come back to this in a second. So now at least we know there are solutions, and now we have this sum of symbols. We want to think about more general situation in higher dimensions. Let's say I have a variety with an action of the Abelian group, and I want to produce an equivariant birational invariant, so I have to understand what happens on the blow-ups, and I want to declare the difference to be 0 after I blow up. Okay, so, well, it turns out that even though there are so many things I can blow up g orbits of points or curves or whatever, all of these things follow from the relations on this slide. And the relations on this slide, they say the following. Okay, I'm consider the free Abelian group on these kind of symbols. The relations are, first of all, permutation, up to permutation of symbols. Secondly, the characters have to generate the group of characters. Next thing is the relation that we had for P2. Well, it sort of percolates. I only look at the first 2 terms, and I apply the same relation. A1, A2 is A1 minus A2, A2, and then it continues, and A1, A2 is, and here it's like A1, A2 minus A1. You'll see in a second. Yeah, so this is the relation, and well, there is sort of one more relation that, well, if A is equal to A1 is equal to A2, AA is like A0 from before. Now, so what is it? In fact, it's exactly as you said. I blow up an isolated point, like on a plane, with a stabilizer, my group G. And so what happens after I blow up? I get 2 fixed points. And then I compute weights at those fixed points. That is precisely the computation of those weights. And if I have AA, then what happens under A? Then I get a stabilizer A along the whole curve. And if I have it along the same curve, I have like A and 0 in the other direction. So this is what happens. And the miracle is that once you know what happens on a surface in an isolated point, you know everything. So in all dimensions. So all the relations boil down to blowing up a point on a surface. Okay. Now, as I said, the relations, it's now, let's say, B3, so it's ABC. So if I'm looking at the cyclic group Z mod P, like a P cubed of those, but then for each time I pick 2 of those, I have these relations. So I have way more relations than I have generated. So a priori, it's not even clear there are any solutions, but then you run the computer and you find something like this for P at least 5. So, okay, well, again, 24. Why do we get 24? And then P minus 1 over 2. So you run the computer and suddenly there are jumps. There are jumps at 43, 59, 67. There are extra classes that come in, and you have no explanation. So, well, it turns out that actually these groups are closely related to cohomology of some specific congruent subgroups of GL and Z. So in particular, that formula that I showed you at first p squared minus 1 over 24 plus 1. Well, that was the dimension of h1 for the modular curve x1 of p. It so happened.
You mean Garland results by Garland, right?
No, that's not Garland at all. So, no. Calculations, I mean. So this is, this is modular symbols more than, this is Manin symbols. So in dimension 2, you see these relations AB is A minus BB and so on. Well, you start analyzing this and then this is what you find. But it's actually more than that. So once you start thinking about the structure, the arithmetic structure of these groups, well, you discover that they carry Hecke operators, that they have some multiplication, co-multiplication, when you look at exact sequences of subgroup, group, quotient group, and so on. So there is very intricate structure in the picture that's of independent interest. But, well, we can, in particular, use them to compute the invariants of actions. Now, how do we do it? Well, as I sketched, you look at the decomposition of your fixed locus into strata. For each locus, you pick any point in that stratum, you record the weights in the tangent space at that point, and then you look at this sum, a finite sum, and now you view it as an element in the group B and G, defined by these kind of symbols, modulo the relations that I wrote down. And so the theorem is that this is an equivariant birational invariant. You can use this to produce obstructions to the irreducibility, and you can analyze it further. All right. So then you think, okay, we understand abelian groups. How about non-abelian groups? Finite non-abelian groups. And we understand that, of course, we look at fixed locus, but sometimes you have loci where the stabilizer is not the whole group, but the subgroup. Well, you also want to account for those. And so the most general setup is in my joint work with Andrew Crash. So we look at this Bern NG. It's a group on symbols. So H is an abelian subgroup of your non-abelian finite group G. Z is a subgroup of the centralizer of H and G modulo H. So there is some field here, some function field of a stratum that we will see with the generic stabilizer H. And beta is a collection of characters of H that will show up in the normal bundle. So, and then you have to write down relations on these things. And of course, one of the relations is obvious. So the conjugation relation, because, well, and then the characters here are up to permutation. So there are some obvious relations. And then there is the blow-up relation. And the blow-up relation, again, miraculously, just comes down to blowing up a point on a surface with an abelian stabilizer. So the blow-up relation will be exactly like the one I showed you, except since we are now looking not only at full stabilizer, but also, some intermediate stabilizers, subgroups. When we blow up a point, we get 2 points with maximal stabilizer, and then the exceptional curve may also have some stabilizer, and that you record as well. So that's the blow-up relation. Once you understand the surface case, you understand everything. Now, so here is a group on generator symbols and so on, and of course the ground field enters into the definition, and well, it proves that there is a specialization homomorphism for this group. And just as a side remark, you can develop a similar formalism of Burnside groups in the context of the Lin-Mumford stacks, where of course you have to talk about what it means to be birational, and also varieties with logarithmic volume forms. And again, what does it mean for a pair, variety and logarithmic volume form, to be birational to another pair? Well, you want that there is a common blow-up, so that when you pull back the form in this form, you get the same. So, and again, there is Born-set formula, specialization, and so on and so on. But let's return to the situation at hand. We have a finite group acting, and it turns out that we want to compute the class of the action in the Burnside group that I defined with generators and symbols on a nice model. And the nice model in this setup is the following. It's a smooth projective model to begin with. So the action is regular on that model. There is a normal crossings divisor so that on the complement to it, the action is free. And for each stratum in the boundary in that divisor, the following property holds. Either G, an element in your group, moves divisor to a disjoint divisor, so a disjoint piece, or you are inside the divisor. So you don't want to swap things that intersect, in other words. Okay? So this was known in equivariant geometry for a long time, that such models exist. Once you reach such a model, every subsequent equivariant blow-up preserves the model. And so on that model, what you know is that all stabilizers are abelian. Now, so having such a model allows you then to write down an element in the Burnside group as follows. You pick that model, each stratum with a non-trivial stabilizer, you write down the stabilizer, which is abelian, the generic stabilizer. Then you look at the residual action on that stratum. Now just think through this. What happens? So you pick up some stabilizer. Your group action has to go somewhere. Well, it will produce potentially several copies of your stratum, but you don't record the several copies. You just record one. And then on that one stratum, you could still have an action. And that's the residual action that goes in here. So when you go from one representative of the orbit to another one, you conjugate the stabilizer. So therefore, the relations, the conjugation relations account for that. And of course, well, to still act on the stratum, you have to be in the centralizer of the stabilizer. And that's what you get here. And these here are the characters of your group in the normal bundle to that stratum. So this is sort of a finite sum. And by the way, H trivial is allowed. H trivial would correspond to the whole variety. So here you would have 1. G, the full group, would act on the function field of the whole variety. You start with the variety with the generically free action, and then the beta would be simply empty. Okay, so you look at this thing, and now view it as an element in that Burnside group defined by generators and relations, and it's an equivariant birational invariant that allows to distinguish actions. Now let me stress right away, we talked about cohomology, and I mentioned that cohomology, H1, is a stable birational invariant. It doesn't change when you multiply with projective space. These invariants are highly unstable. In fact, there is an M that only depends on G, so that when you multiply with projective space of dimension at least M, everything vanishes. Okay? So it's kind of orthogonal to what was used before and studied before. Very unstable thing. Now, of course, you could start, okay, since I know that, maybe I have times P1, times P2, I can get some kind of filtration on my invariants and so on and so on. But this is what we have. And, well, we can try to apply it. So let's talk about some simple applications, let's say threefolds. There is something called the Burckhardt quartic, like a very singular thing. So you take a symmetric polynomial of degree 4 and 6 variables, like x1, x2, x3, x4, plus all the other things. And then you take x1 plus x2 plus x3 plus up to x6. You get some very singular quartic, happens to be rational. So you can ask, well, I look at some subgroup of the symmetric group that acts on, well, when is that action linearizable? Now, rationality of forms over non-closed fields of the Burckhardt quartic, that was actually studied by Caligari and Shiva Shidam Baram. It's relevant. You look at like moduli space of abelian surfaces with special structures and so on and so on. It was interesting for their applications, and so in particular, they computed all Galois actions with non-trivial H1. So there is some table in their paper. Well, but we can also look at this equivariantly. Suppose our group contains an involution ij, like 1, 2. And let's look at the fixed locus for the 1, 2 involution. And so what do you get? You have a very singular quartic, and now you have a fixed locus for that. And that happens to be a quartic surface with 12 nodes, a K3 surface. So when you start recording in that Burnside group, you find in symbol C2 stabilizer, the quartic, K3, and of course C2 can only have one in the normal bundle, and that symbol will appear on every birational model. It's a divisorial symbol, and the quartic, of course, it will be carried along. And when you look at linear actions of C2, of course, you never get anything like this in the fixed locus in any of the stratifications. So that symbol will tell you that the C2 action is not linearizable, and therefore any group that contains this involution is not linearizable either. This is a very simple thing to see. How about M06 bar? So in its Segre cubic model, so it's a sum of cubes equal to the sum of coordinates, and now you see the S6 on it. So now over the reals, every form of this singular cubic threefold is rational. Now there are non-rational forms over other fields, and Florence Reichstein studied this. They presented some examples. Now, in like birational geometry, covariant birational geometry, birational rigidity, it was known that the full S6 and A6 actions are birationally rigid. Now, there are like S5 and A5 inside, and they're like a standard one and a non-standard one. A standard one would, act in a standard way, coordinates, and then there's the other one, and one of them is birationally rigid, and the other one is linearizable. It's kind of funny. And, well, in recent, yeah? It's a Borg card, it's not the Iguni. It has a bigger, it's a Borg card. I think it's a Borg card. Well, okay, but how I called it doesn't matter, the equations are there. Yeah. Wikipedia calls it something else? Okay, well, now, but with Segre we are in agreement, yeah? Okay. Now, so we have like a complete analysis of all the actions. So in particular, we know when the action is linearizable, well, of course, if my action fixes a singular point, then I can, as before, project from the singular point, and, well, I get linearizability or rationality over non-closed field. But the answer here is that it's linearizable if and only if it's stable linearizable, if and only if the Picard of a resolution of singularities, which would be M06 bar, is a stable permutation module. So this is in the equivariant context, and then you can do it over non-closed field. And again, the answer is the same for the Galois action. So, and the way we proceed, of course, we analyze all the cohomological abstractions, but there are also some abstractions coming from this Burnside invariants. Now, inspired by this, we started thinking about, well, other singular cubic threefold. So, for example, well, it's known that a smooth cubic, or an algebraically closed field, of course, is non-rational, but a singular cubic with isolated singularities of an algebraically closed field is rational. And so we can look at the symmetric ones. And Viktorova in 23 produced a complete list of all possibilities for isolated singularities on cubic threefolds. So we look at those tables and we extract all symmetric ones, all those that admit actions, and then we give a complete description of G actions or Galois actions on the Picard of the resolution of singularities and using Bern set invariants and using everything inside. So this is sort of the geography of things that you have. So you have like cubics with 2 nodes and you have all the other ones. And then, well, you can see how these things specialize. You can make things worse and worse and worse. And we haven't covered all the cases, but pretty complete description of what we can do. And so finally, how about some examples? How about cubic threefolds over R? Well, if you have cubic threefold with 2 A1 singularities that are, well, in the complex conjugate, so the 2 of them together are defined over R, but not individually, then it's not rational. Stable rationality is known. And so here is another example. How about a cubic threefold over Q with 3 D4 singularities? And so here is an equation, and this one fails stable rationality. All right, so, and where do we get it from? Well, so we can look at the C2 action on everything inside, and we can produce C2s that have cohomology. And then we can look at those that specialize to those with cohomology. So like in 6A1, 8A1, 2A5, specific C2s sitting in the automorphisms of those have homology, in this case for C2, and in this case for C3. Like this is the case of 3D4. The example that I wrote down has precisely that action that would give you homology in H1. It would prevent stable rationality of that cubic. And well, then there is specialization. And so once you see this thing, you get the following theorem in the equivariant context, that a very general member of a family of, let's say, G cubic threefold, where G contains the C2 or the C3 from the previous slide, that would specialize to cohomology, the very general member would fail to be linearizable for that C2 or C3, stably linearizable even. But here's the funny thing, that over a non-closed field, that very general doesn't apply. It fails. So in particular, we have no such conclusion over the reals. And so we can look at singular cubic threefolds over the reals. Well, of course, one abstraction to rationality or stable rationality would be, well, how many connected components? But suppose it's connected, well, which ones are rational, which ones are not? So that's still puzzling open problem. To summarize, there are strong analogies between equivariant geometry and geometry over non-closed fields. Well, there are some new invariants based on ideas, localization, motivic integration, and so on, that allow to solve some outstanding problems in this field. All right, so that's the end of my talk. Thank you so much.
Is there any question?
Yes, so the question was, are there generalizations to algebraic groups rather than finite groups? Indeed, you could think, well, how about tori acting, algebraic tori? Or how about like PGL2 actions and so on? Well, there are some subtleties. So when you act with tori, you always have a slice. So in other words, it's basically the quotient variety times the standard torus. So that's not that interesting because it will basically boil down to stable rationality problem for varieties without any actions. If you think about PGL2, another issue comes up, namely, as you move along a stratum with non-trivial stabilizer, the group can change continuously, the stabilizer. So that's a nightmare. Now, what is interesting and what might lead to new invariants would be extensions of tori by finite groups. That case is interesting. Then you get something. You get sort of a mixture of this and that is certainly something that could be explored. And you would do the same thing. You would look at strata with stabilizers, and then you would look at what happens in the normal bundle and residual actions and so on. Such a group exists, makes sense, but we don't have geometric applications in this context. Yes?
You mentioned intermediate Jacobian, initial question. But obviously, in some cases, you can practically eliminate them, and you can, using your basic integration, you can prove the same, right?
No.
But no.
No. It's yet another type of invariance, intermediate Jacobians, and indeed there are some equivariant refinements of the theory of intermediate Jacobians in my recent joint paper with Schotter and Muta, and it's complementary. You get torsors of intermediate Jacobians, and those torsors are equivariant invariants. They persist, and you get all kinds of interesting geometric consequences of that theory. But indeed, like G-Hodge structures, fully explored really, and well, some new abstractions come about of a different type, not like this. Yeah.
Any other question? Maybe I can ask a question about the irrationality. So I think maybe in your talk, you also learned about just stably rational invariant. So my question is that can you combine the new possible truths for proving that a stably rational variety which is not rational other than the intermediate Jacobian, which goes way back to 150 years ago?
Yes. So the question was over non-closed fields, there are of course Filpezzo surfaces which are not rational but stably rational. So there was use over complex numbers. There are some threefolds. The work of Bouville, Coulot-Telent, and Zixon and Dyer, complex threefolds that are not rational, where you would see the non-rationality via intermediate Jacobians, but are stably rational. In presence of group actions, we produce many, many examples of non-linearizable but stable linearizable actions beyond those that were already on the slides. The work of Reichstein and Houston shows that if you take two, first of all, you have non-birational representations of abelian groups, and secondly, any two representations are stably birational. We produce many stably linearizable actions on cubic threefolds, on cubic fourfolds. Indeed, in the equivariant context, it's much, much easier to come up with stable linearizability than it is over non-closed fields. Yeah.
Thank you. Any other question? Okay, if none, then let the speaker